last time what we saw was that, well, the notion of black hole really does need general relativity. Newtonian gravity and Newtonian mechanics are conceptually insufficient to talk about black holes. There are no black holes in Newtonian gravity and Newtonian mechanics, in spite of the claims made in the early days by Mitchell and Laplace and these people. The other point I just told you was that how surprising it is that in fact, whereas if you look at static stars, they can have a lot of multiple moments, they can be oblate, prolate, but a static black hole, the uniqueness theorem says that it is really just a Schwarzschild black hole, so it really is spherical symmetric. So static non-rotating black holes are uniquely known, and similarly rotating black holes in 4 dimensions are uniquely known to be Kerr solutions. As I emphasized, there are many solutions which are static gravitational fields, which are not spherically symmetric, and similarly there are many solutions of vacuum equations which are not Kerr, which are stationary and axisymmetric. Okay, so we saw that last, in detail last time. So therefore, please don't think that Kerr is a unique solution. If you have a star, it is not, the exterior field is not represented by the Kerr metric in general. In fact, one does not know how to fill the Kerr metric with a perfect fluid solution. So this is what we saw last time. And now what we want to do is we wrote down also the Schwarzschild metric, and I told you a little bit about how big confusion there was for decades about the singularity structure. So again, historically, this is not how Schwarzschild wrote down the metric, but soon after that, the metric was written as 1 minus 2m over r, and r squared in a spherical symmetric form, plus d squared plus r squared minus 2m over r times angular unit to sphere line element, which is just sine squared theta d theta squared plus sine squared theta d phi squared. By the way, I did mention before that I know that people in mathematics may find some of the things too heuristic and may not have some issues with it. So please don't hesitate to ask questions for clarifying, do you mean this or do you mean that, etc. Okay. So this is the form of the metric, and we see immediately here that r is equal to 0, r equal to 2m, where probably the metric becomes ill-defined, this coefficient vanishes, so metric is degenerate, this coefficient blows up, so the metric is not at all well-defined, and this for the longest time was known as the Schwarzschild singularity. And now, why is it so difficult in general relativity? But where is the singularity? But I also told you last time that this is not the case. There is no problem at r equal to 2m, and we're going to see this in great detail next time. But the question is really, what is the singularity? Why is there a problem? I mean, why can't we? So there are 2 issues here about what is singularity. The first is that consider, for example, Maxwell fields. And if in fact we can just look at the FAB, this is the Maxwell field tensor. These are space-time indices, right? FAB up here. And if in fact components of this FAB in a Cartesian chart if the components of FAB in a Cartesian chart diverge, then we know that this is singular, that the Maxwell field is singular. This is clearly something that we can just say that, well, that's a singular solution. There's no two ways about it. These are Maxwell fields in Minkowski space, I should say. But our problem is that we don't have Cartesian component. We don't know what good coordinates are a priori in general relativity. In Minkowski space-time is given to you, and we know what Cartesian coordinates are. So the first problem that comes up is what are no preferred coordinates. So even in Minkowski space, we could use some chart, some coordinates which are related to the Cartesian coordinates by singular transformation, And if in that coordinates FEP blows up, we are not concerned. We say, well, it's a problem with the coordinates, not with the field strength. We should look at the components of a good chart. But what do we mean by good chart? What do you mean by good coordinates is something that we do not know in general relativity. That's the first goal. And the second thing, which is common to everything else, all fields, is the fact that we now have space-time structure. And in space-time structure, the metric is of indefinite signature. So one might imagine that what I should do is to look at, to avoid the components, one often says that what we should do is to look at invariants. So we could look at invariants, for example, FAB, FAB, or FAB star FAB. So FAB, FAB is just E squared minus B squared. In the Cartesian coordinates, it will be just, if you give a slicing of space-time into space and time, you define electric magnetic field, it will be just E squared minus B squared. And the problem here is the following, that namely, if I just look at these invariants, then this is not a positively definite quantity. And therefore, it could happen that E blows up and B blows up, but E squared minus B squared is perfectly fine. And therefore, just looking at curvature invariants, you cannot determine what is actually singular behavior or not. And in particular, in gravity, we do have solutions in GR with singularities for which all curvature invariants vanish. So it's like E equal to B in this case. So in general relativity, you have got a Riemann tensor, and we can have solutions to Einstein's equations. There are solutions to Einstein's equations which are kind of given, which are explicitly known, which are, there is a genuine curvature, but in which all curvature invariants vanish, and yet there are singularities in a sense that we'll discuss as we go along. And therefore, this is a problem. The problem is basically you cannot look at components because there are no preferred coordinates, and you cannot look at invariants by themselves because of the indefiniteness of the signature. So I'm going to give you some trivial examples to see what one does. So if you're given a metric, you ought to know, is there a singularity or is there a coordinate artifact? That's what we want to know, right? And so let's do very simple examples. These are mathematical examples. So let's start with the Riemannian signature, plus signature. And for reasons that will become clear in a minute, we're going to look at just two-dimensional metrics. So the first example is just look at the metric in which ds squared is equal to dx squared upon x to the fourth plus dy squared. Take this as a simple example. And now it's clear that the metric is bad at x equal to 0. Therefore, let's suppose that x is in 0 infinity. This is your manifold. And y is in minus infinity to infinity. So it is a half plane. There is a manifold on which there is a metric. And anybody looks at it says, oh yeah, this metric is singular clearly at x equal to 0. But it's not really the case, because I can just define a new coordinate, x tilde, to be equal to 1 upon x. And then dx tilde is equal to 1 upon x squared times dx. And therefore, when I take the square, I'll just find that ds squared is equal to dx tilde squared plus dy tilde squared. Okay. So this metric is just a flat plus dy squared. This metric is just a flat metric in the x tilde y tilde coordinate. But of course, x tilde now goes from 0 is, so x tilde will be equal to infinity up here. X tilde equal to x equal to 0, so x tilde will be infinity. Yeah. So this goes from infinity to 0. So it also goes from 0 to infinity. It goes from infinity to 0 here. It also goes from 0 to infinity. And what has happened is that the singularity that we had at x equal to 0 is just moved to x equal to infinity. So nothing much has happened yet. But if we look at this metric and we say that, well, wait a minute. Why are you so silly and restricting x tilde to go from 0 to infinity when the metric is clearly well defined, for negative x values? So we can now extend. So this is the new thing. Up to now, I just didn't do anything. I just wrote down the metric in another coordinate. But this suggests now that we extend space-time or extend the manifold. And we extend it so that x tilde now takes values into minus infinity to infinity. So if it takes values from minus infinity to infinity, now we're in good shape, right? Because now the metric is completely flat, and clearly now the new manifold is larger than the bigger manifold, right? So the metric is now. So the interesting thing is what happened here. Well, if I go to from x tilde to minus infinity to infinity, what happened to x, if you like? So previously, we thought that the problem was really at x equal to 0. But in fact, the problem really was at x equal to infinity. Because, x equal to infinity. Because at x equal to infinity corresponds to x tilde equal to 0, and we could actually extend it beyond that. So counterintuitively, the problem was at x equal to 0. X equal to infinity. Not x equal to 0. So x equal to 0 just is move to x tilde equal to infinity, and then the metric is, that is defined perfectly fine. So that is where the problem was. And we could also see it. And the check for this is we can look at geodesics of the metric, of this ds of the metric. So this is an exercise. So anytime there's an exercise, people, especially people who are taking it for credit, should really do it. You calculate the geodesics of this metric that were given to you. They're very trivial to calculate if you go to this coordinates if you like, but you can calculate also the old coordinates up here. And you will see that the old manifold is incomplete. In other words, we got geodesics which run, their length is finite, and yet the geodesic terminates in this chart up here. And therefore, all we have done is that, well, no, we just extend this geodesic, we just extend the manifold, we got a bigger manifold, and what we are saying now up here is that, in fact, the old manifold was small, the bigger manifold, everything is well defined, and that manifold is just flat. So that is the first example. It's a very trivial example, but it tells you that we should really look at something like geodesic completeness. So this is the important point that we're going to look at. So new manifold is basically complete. And one measure of a singularity is really that if you cannot do this extension, if the metric is such that the space-time manifold cannot be extended and some geodesics are really incomplete, and that is when we say that there is a singularity. So that is a general idea. So let us take a second example. This second example is even simpler. Just given by dx squared. Is just given by x squared, dx squared plus dy squared. And again, x is 0 to infinity, and y is minus infinity to infinity. So the second example is this metric up here, and the range of coordinates is given up here. And again, it might look like there is a problem at x equal to 0, but just staring at it, we see that there is really no problem. We can just define x tilde as a new coordinate to be x squared divided by 2, and then the metric is just given by dx squared is equal to dx tilde squared, dy squared. X tilde is again from 0 to infinity. So again, nothing has happened, it is just up here. But now we see again that the manifold can be extended. So we extend the manifold. This is a non-trivial step. Trivially. And if we extend the manifold to that, then we have just obtained x tilde minus infinity to infinity. And again, you can see that this new manifold is geodesically complete. So this is something that people should check, that the new manifold is geodesically complete and the old manifold is not geodesically complete. So you can just calculate the geodesics of this particular metric and you can see that in fact this space-time that I given to you up here, this manifold, if I just have x 0 to infinity, in fact you have got geodesics with finite length, or if you like, finite affine parameter. I'll just say what is affine parameter in a second. And what we have done is we just extended it through x equal to 0 and therefore obtain metric which is geodesically complete. Now this may look a little bit familiar. So up to here everything is okay. I mean, these are all very trivial examples, but it makes you think that just because you see that there is something problem, it doesn't mean that there is necessarily a problem. What we should do is to actually, of course, one possibility is the following. You sense that there is a problem and you can calculate curvature invariance like FAB. If a curvature invariant does blow up, then there's a problem. Right? But if it does not blow up, it doesn't mean that there is no problem. So we do not know that. So that is the main point up here. So you can calculate the curvature invariant. If it blows up, then there is a problem. Then we stop. That means that this is space-time that is a genuine singularity. But if the curvature invariant does not blow up, then we can see if in fact we can extend this manifold. We might be able to extend it. We might not be able to extend it. And a good idea is to use geodesic completeness. Now there is a simple sort of example up here, which is just take this flat metric and write it as in Cartesian coordinates as r squared d theta squared plus dr squared. Right? Just write in this particular coordinates. And again, the statement up here is that it looks like there is a singularity at r equal to 0 because this is 0, and therefore the metric becomes degenerate. It's not well defined. But we know that r equal to 0 singularity is spurious. This is just spherical. This is just the spherical coordinates in 2 dimensions, and we know that we can just write down x to be equal to r cos theta and y to be equal to sine theta, and then this metric is just dx squared plus dy squared, and r equal to 0 will correspond to x equal to 0, y equal to 0, and there is no problem here with this metric at all. So these were bad coordinates. I just want to tell you this, that these are bad coordinates. It's just that we've gotten used to using them. They are bad coordinates, and keep in mind, yes, I know they're bad. If when in doubt, I can always go to Cartesian coordinates and then check what happens up here. So sometimes we do this, and we maintain the bad coordinates because they're easier for calculations or whatever it is, and that's perfectly fine. There's nothing wrong with it at all. But if you are in doubt, then always find good coordinates with respect to which the space-time is complete. If I cut out r equal to 0 point up here, saying that there's a bad coordinate, then in fact that space-time is not complete, because you can adjust x direction geodesic, and it is going to end at a finite distance at r equal to 0, right? Or y direction geodesic is going to end at finite distance. You start at y equal to y naught, go to y equal to 0, so only the length up here is just y naught, and it's incomplete. And we see that it can be, there's no problem at all. This was just a problem of these coordinates. We can extend the manifold by adding r equal to 0 point, and there's no problem at r equal to 0 point. Okay, now the third example is sort of the beginning of Lorentzian example. And this example will pave way to understanding what Kruskal did for this particular metric up here. And this Lorentzian example, you just write down the metric to be equal to minus z squared dt squared plus dc squared. Those of you who might have sort of noticed that there is a kind of a similarity here. Z is like r, and t is like theta up here, if you like. I mean, of course, there's a minus sign. That is because we are looking at a minus Lorentzian metric up here. So this metric also looks, in these coordinates, it looks like bad at z equal to 0. It looks singular at b equal to 0, and we want to know if it is in fact really singular or if it is not singular. Now the point was that for these examples, which were just Euclidean examples, we could just take any old geodesics and complete and see what happens, right? Because all geodesics are on the same footing. You don't have time-like geodesics, space-like geodesics, null geodesics, etc. In 2 dimensions, and very often 2-dimensional spaces are going to be important. In 2 dimensions, what happens is that it is very convenient to use in the Lorentzian signature. It is very convenient to use null geodesics to test all these things. So this is, I'm not saying this is a theorem, I'm saying this is a strategy that we all use, that is standard thing to do. You get some unfamiliar metric. For example, in the 1980s, I was looking at a C metric, which was discovered by Levi-Civita. Ultimately, it turns out to be kind of describing 2 black holes, which are constantly accelerating with respect to each other. And again, looking at the form of the metric that was given, it was not at all obvious. So the question was, can we extend it? Can we do something? And this is the kind of tricks that we play. We look at null geodesics and then see that, in fact, yes, you can extend it, and then see how much you can extend it and so on. So this is really the kind of a very standard tool in your toolbox that you should have. And that is really looking at null geodesics. But also in 2 dimensions, all metrics are locally conformally flat. Now this metric is in fact globally conformally flat, because I can just take out the z squared as a conformal factor, and I just get minus d squared dz upon z whole squared. Okay. I've not done anything, I just written it in a different form, which is conformally flat up here. And this is the conformal factor, and this is a flat metric up here. So this tells us that we should define perhaps a new coordinate zeta to be equal to log of z, or z is equal to e to the zeta. Therefore, this coordinate will just be equal to, so then here I will get here e to the 2 zeta times minus dt squared plus d zeta squared. Okay. I've not done any real thing up here, it's just that I've written it manifestly flat. So this is manifestly flat. And this is a conformal factor. Of course, at z equal to 0, zeta becomes minus infinity. Therefore, this conformal factor goes to 0, and therefore the metric is actually bad. So I've not done anything new. I mean, the metric is still bad at z equal to 0. It's just the singularity is sort of pushed away at the zeta equal to minus infinity. So this is a conformal factor. This is manifestly flat. And now, as I was telling you before, in 2 dimensions, it is convenient to use null coordinates. So we define new coordinates called u and v. So this little u, lowercase u, and lowercase u is just given by t minus zeta, and then v is given by t plus zeta. So remember, all this exercise, what are we trying to do? We are trying to understand the invariant structure of the metric that is given to you, of the space-time that is given to you. And that is what is essential to extract physics, right, in general relativity. So that is our goal up here. So little steps up here might look trivial, but really there is a soul to these little steps that you should keep in mind always. So if I do that, then of course minus d zeta squared plus minus dt squared plus d zeta squared, that is just equal to, let's see, minus du dv. This will be equal to minus, these are all little, du dv. And then I got e to the 2 zeta. And e to the 2 zeta, just from here, is equal to e to the v minus u. Again, so far I have not done anything. I kept the old manifold. I have not done the extension of the manifold at all. But now I would like to know if in fact this manifold that I got is geodesically complete. So this is again exercise for students. Check that this is that null geodesics are not complete. Now I have to say what I mean by this. Okay. So what you can do is you can look at the null geodesics of this metric up here. And so you would like to look at geodesics. So this is equal to 0. This is called affinely parameterized geodesics. If I take eta tilde A to be equal to alpha times eta A, then eta tilde A grad A, eta tilde B up here. If I just rescale it with this factor up here, so that will give me alpha times eta A grad A, alpha times eta B. So when alpha comes out, I get eta A grad A eta B, which is 0. When alpha stays in, I get here alpha times eta A grad A alpha times eta B. So this alpha with this eta B just eta tilde B, and I get here eta A grad A alpha. So if I just rescale this vector field by a function, I get a new vector field. That new vector field satisfies almost the geodesic equation. Sometimes this is called the geodesic equation, that eta A grad A eta B is proportional to eta. But when it is affinely parameterized, then eta satisfies this condition up here. And then what you do is you look at affine parameter. This is not unique because you have freedom of choosing the origin where the parameter is equal to 0. Let's call this affine parameter F, say, or what is a good name for it? Let's call it U. So it could be one of these U's, for example. Then this affine parameter U up here. So then the statement is that, I mean, this has nothing to do with what I'm doing here. This is completely general. Let's just call it, let's call it beta. So therefore the statement is, what it satisfies is just eta A grad A beta equal to 1. So you first look at affinely parameterized geodesic, that is to say eta A grad A eta B equal to 0, and then look at the affine parameter, which is just this beta, which is its parameter along the vector field. So eta A is just d by d beta. That vector field is just d by d beta. So you do that, and then we ask the question, is the geodesic complete? Does the parameter go from minus infinity to infinity? If you got a geodesic which is time-like or space-like, you can just ask, is the length of the geodesic go from minus infinity to infinity? But for null geodesic, the length is just 0. Therefore, we cannot use the notion of length. So we use this notion of affine parameterization. And if you use this notion also for time-like or space-like geodesics, you will find that, in fact, if geodesic is complete with respect to its affine parameter, then it's also complete with respect to its length. So the two things are complete, are equivalent to each other. But for null geodesic, this goes up. So what I'm asking you is really calculate the null geodesics of this thing. And take a hint, they should be like proportional to d by du, if you like, and then d by dv, because these are the null coordinates. And then say, in fact, are there, if I just take those vector fields, you will find that with those vector fields, this is not affinely parameterized. You have to rescale them with some factor, and when you rescale them with the factor, you'll find that the geodesics are not complete. The affine parameter does not run from minus infinity to infinity. But there's a very simple trick now, namely this form the metric suggests that we should absorb. You see, if the metric was just this, if we had a metric ds tilde squared, say, different metric, which is minus du dv, this is just a flat metric. This metric is just minus dt squared plus d zeta squared, where t is going from minus infinity to infinity, zeta is going from minus infinity to infinity, and therefore it's just a flat metric, and of course complete, there's no problem at all. The problem is all coming because of this conformal factor. In other words, the curves, which are geodesic curves of this metric, are the same as the geodesic curves of this metric. Null geodesic curves of this metric are the same as the null geodesic curves of this metric, because the two are conformally related just by conformal factor. But the affine parameterization is not the same. In other words, something which looks affinely parameterized with respect to this metric, eta A grad A eta B equal to 0, would not satisfy the eta A. With respect to this metric, if I take a vector field eta A grad A eta B equal to 0, then in fact eta A grad A eta B is not equal to 0. It is proportional to eta B, and this is non-zero. So the null geodesic with respect to the flat metric are not affinely, they are affinely parameterized with respect to the flat metric, but they are not affinely parameterized with respect to the physical metric that I got because there's a confounding factor. And so you can check that is the case. And that is the reason why you will have to multiply this vector field d by eta vector field by some suitable function to actually get an affinely parameterized geodesic with respect to the physical metric. Is this point clear, Monica?
Yes.
Yes. Good. So this is all clear. So that then we can just continue up here. And so the statement is that now the trick up here is very simple trick. Just like what we did here, we just define new coordinates. So we can just define e to the v to be equal to big V. And I can just define e to the minus u to be equal to du. Let me just check it's minus u or minus u. So we just define this, and then we just get here our metric dA squared, or the metric up here is just equal to du dp. And this is perfectly fine now. Right? This metric is now really flat. We see that this metric is really flat. So the physical metric was conformally flat, but it is also flat. It's just regular flat up here. It's just that in this form, it is not obvious it is flat. This confound factor is very special. And in fact, the curvature of this metric is 0. We could not see it just looking at this form of the metric, but in this, just doing this, we see that the curvature is obviously 0. Right? Because just du dv is just looks like 2 minus du dv. It just looks like the Minkowski metric. But what are the ranges of u and v? Well, little u and little v, because t goes from minus infinity to infinity, and zeta also, little u and little v, they both go from minus infinity to infinity. But what about big U? Well, big U, or let's just say big V first. What about big V up here? So, right. So when this is equal to infinity, big V is equal to infinity. When little v is equal to minus infinity is equal to 0. So big V goes from 0 to infinity, and big U, because of the minus sign, goes from minus infinity to 0. So what has happened is that we are given the original metric, we are given the original metric, right, the original metric that was given to us up here, and we reformulate the metric in this particular form. But now we see that this big U and big V only cover part of space-time. Now those of you who are looking at to check about null geodesic completeness, it is obvious from this part that the null geodesics are incomplete because I finally parameterized null geodesics. The vector field there, eta A, is just given by eta A dA equal to d by d big U, and so eta 1 equal to that, and eta 2A. So d by du and d by dv, the big V, are just affinely parameterized geodesics. And the affine parameter is incomplete because u and v just go from 0 to infinity, minus infinity to 0. So basically, I can start at some finite value of v and run to 0, and I will find that the geodesic is my space-time ended, but the geodesic affine parameter was just fine, was just finite. It was not infinite at all. But I mean, it's obvious now what we should do. We should obviously extend this, right? Let v go to minus infinity, let u go to plus infinity. So this is the non-trivial step that we take, which is extend the space-time So this is the step that we're looking for, which is extend the space-time, and then see what happens when we extend the space-time. Well, what is happening up here when we extend the space-time? So to understand it, I mean, we can just draw this, but to sort of put it in the familiar language, at least to physics people, we can just introduce Cartesian coordinates. Think of them as null coordinates. So just as here, where t minus zeta and t plus zeta to be the null coordinates, we can now introduce Cartesian coordinates, capital T and capital Z, such that u is equal to t minus z upon 2 and v is equal to t plus z up to 2. So if you like, t, so therefore t up here would just be equal to this, right? So t up here would be equal to u plus v. So I should do the other way around, right? So t is equal to u plus v is equal to, yeah, and z. So just introduce Cartesian coordinates, and then when I use this, it's really following what we had done before, and then this metric dA squared that we have, which is just minus du dv, just becomes minus dt squared plus dz squared. These are the capital ones, t and z. So it just becomes this flat metric, and of course t and z now goes from minus infinity to infinity. Now again, students who are seeing this for the first time, this may be going a little bit fast, but please go to the notes and go through all the calculations in the notes, convince yourself that that you understand this subject very well. But this is really spelled out in great detail in the notes which are on the web page. So let us look at these coordinates t and z, which are the final coordinates we arrived at. So here are the coordinates t and z. So it's a two-dimensional Minkowski space with metric to be minus dt squared plus dz squared. Could not be more boring than that, right? I mean, just ordinary Minkowski space. The only non-boring thing is that it is an indefinite signature. I mean, okay, and then u equal to 0 and v equal to 0 are just these curves. This is v equal to 0. This is u equal to 0 because u is equal to t minus z. So u equal to 0 is t equal to z, and then the other one is this. And what we're seeing up here is that the original manifold that we started out with, the original manifold only covered v, which are positive, and u, which are negative. So the original manifold covered u negative, so in this region. But v is also positive. So the original manifold was only one quadrant of this Minkowski space. It was not all of Minkowski space. Right? And what we did here via these extensions is to realize that was just a stupid coordinate limitation of choosing bad coordinates up here. That we really could extend the manifold without any problem, and then we get this bigger manifold up here. This is the original wedge. So now you can look at, I just leave this as an exercise because it's pure algebra and also done in detail in the notes, that not very surprisingly, we saw that there is a very good similarity between this and this. Right? Z was like r, and t is like theta. So t was an angular coordinate, okay, here. And here we got signature which is minus plus. So whatever is angular becomes hyperbolic angular. So x, for example, is given by r cos theta. So here the statement would be that that z up here, the good coordinates, is just given by t. Is given by big Z is given by, this is a big Z is given by little z times cosine t, and big T is given by little z times sinh of t. It's very similar to the Cartesian coordinate that we saw. It's just that cos is replaced by cos, and sinh is replaced by sine is replaced by sinh of t. And then you can ask for what was the physics of the old manifold. The new manifold we know everything about. We have got time translation, d by dt, capital T, space translation, d by dz, and we've got a boost killing vector up here. In the old manifold, we only see, because it depends on z, manifestly we only see that there's one killing vector field, which is d by dt, little t up here. So we can ask, what does that killing vector field here look like? So what does d by dt look like? So d by dt just looks like z d by dt. So you just do this coordinate transformations to make sure that this is correct, and this coordinate transformation. It just looks like z by dt plus t d by dt. So this was a killing vector field. It's a killing vector field because the metric here manifestly does not depend on the time coordinate t. That's why it's a killing vector field. So that vector field, when you transform, looks like this. And this is a boost. So our killing vector field d by dt is this vector field. It is just the hyperbolic rotation. In this case, the rotational killing vector field would look like x d by dy minus y d by dx. This is the killing vector field up here. So this will be the vector field d by d theta. This is the vector field that will, and this is the rotation in the Cartesian coordinates up here. This is a rotation expressed in the Cartesian coordinate for a Euclidean metric, and we have got exactly the same thing, except that this minus sign is become a plus sign, and that is the difference between a rotation and a hyperbolic rotation, or if you like, a boost. So our killing vector field looks like this. And this killing vector field becomes null here. If I take this vector field TA is just defined by d by dt. So TA vector field has coordinates. The little t coordinate is equal to 1 and little z coordinate is equal to 0. So that's obvious. Okay. So little TA. In little t and little z chart. So this killing vector field TA up here is null. So this is a null killing vector field. It's a vector field which becomes null on these boundaries up here. And these boundaries on which a killing vector field becomes null, that called killing horizons. I'll write down the definition in a second. What exact definition is in a second up here. These are called killing horizons. So what we see up here is that T along this is the thing on which little z is constant. Little z is constant. So little z is like this distance up here. Let's just use this thing. This is little z, and this little z is the proper distance. Maybe I should expect. Yeah, let me not get this. Okay, so d by dt is this, so therefore t is like the angular coordinate, it actually changes up here, and z is like the radial coordinate. So this is the boost killing vector field. And we see that the old manifold was incomplete because if I looked at d by dt, for example, it goes like that. d by dz vector field, capital Z vector field, looks like that. So obviously, if I take d by d vector field, I'm cutting across the boundary of the whole manifold. The whole manifold is really incomplete. Similarly, d by dz vector field, that space translation vector field, is incomplete. So this little quadrant of Minkowski spacetime is often called Rindler wedge. Which was the original manifold we started out with. We just didn't realize it. We realized very quickly that it was actually conformally flat, and then a little bit later we realized it was actually flat. But what we did not realize is that it's a flat piece of Minkowski space, but it's a proper flat piece. It's not all of Minkowski space, it's only a patch of Minkowski space. And that's what we sort of see here explicitly. So very often, for people like me, working with coordinates is difficult. I sort of struggle a lot, but it is essential in some circumstances where you want to know how big is your manifold. The metric may be given to you in a plate, like Schwarzschild metric is given to us in a plate, but that may not be the most convenient way of actually writing the metric. Right? So we have to really struggle and see if in fact it is complete. So I just want to say one thing and then we'll quit, namely, what are the steps we have done up here? This is all again emphasized in the notes. The first is that you note that there is some problem somewhere, and what we want to know is this a real problem or it's not a real problem? One way to look at it is to actually solve the geodesic equation, actually construct the geodesics, and in 2 dimensions, null geodesics is the best way to do it because the things are conformally flat. So you look at the geodesic and see if in fact the spacetime is geodesically incomplete. If it is actually geodesically complete, then that's it. If it's not geodesically complete, then you try to extend it. And 2 things we did. First was trivial, which is just use convenient coordinates. We don't change the manifold. Don't change the manifold. But then we arrive at somewhere, and then we see that in fact the manifold can be extended. The whole manifold was a piece of the real possible manifold, and then we carry out this extension. Okay. The first thing is to look at where is the problem, check if it is geodesically complete or not, then do some simple manipulations if you can to make the manifold geodesically complete. That typically involves the extension of the whole manifold. Okay, any questions? I don't pause too much I don't pause too much in future. I will pause much more. The reason is because this material is rather elementary and I just wanted to get quickly over it. As we go along and enter more and more difficult material, I will stop at many places and ask for questions. Please.
So your definition of like a singularity, or at least like a, let's say problematic manifold, is one in which you have particles which have a finite length geodesic, right? That's a very particle-based way of like describing singularities, while GR is field theory. So I was kind of wondering, like, this is actually, like, does the notion of geodesically incomplete actually say anything about like solving the field equations?
Right. So the statement is that which field equations? You mean the Einstein's equations?
Right. So for example, Einstein equations.
We are already talking about solving the Einstein's equations themselves, right? So it's not from the beginning. Everything is about looking at solutions of Einstein's equation up here. And so the big question is whether, if in fact you've got some geodesic incompleteness, is it a real singularity or not? That's the question we want to ask. I think the key point I wanted to emphasize at the end of Schwarzschild, I wanted to emphasize this much more, was that we don't have a clean notion, which is written in a little 3-line as to what is a singularity in general relativity. I just want to emphasize that. There's no simple thing that this is what I mean by singularity. There are indications as to where the space-time is singular, and a very strong indication is if it is geodesically complete. But typically then, if it is geodesically complete, you can just ask with respect to the field equations, okay, I got Einstein's equations up to this point up here. Can I extend it? Now, the extensions that were carried out and everywhere, they are of course such that these are our analytical extensions, and therefore of course, if it was Ricci tensor was 0 before, the Ricci tensor is going to be 0 afterwards. It's going to be a solution to field equations, no problem at all. Same thing is going to happen with Schwarzschild and Kerr. These are going to be analytic extensions across the boundary. But in general, it's a real issue. I mean, for example, When we actually get some singularities, for example, in Rice-Nosdam solution and such thing, the question is, can you actually extend it beyond that? And then the question is, what extension do you want? Do you want extension which is C1, C2, C0? Is it extended in the sense of a distribution? Is it extended in the sense of... So these big questions become much, much more important, and these are kind of frontier questions in geometric analysis. People work on it actively. There is a debate about these issues currently about, whether we can actually extend across the Cauchy horizons. These are all, I'm talking ahead of myself, but Cauchy horizons in Rice-Nosdam and curve solutions and such things, because if you allow extension to be just a C0 metric, then the answer is yes. But if you don't allow it to be, you want it to be at least a C2 extension, then the answer is no. So these are interesting frontier questions. So what we're doing up here is really the zeroth order notion of what is singularity. And what we're saying is that simple things which look singular need not be singular, we can extend it. So I'm avoiding the hard questions of analysis here by just saying that, well, there is a larger manifold over which everything is clearly, completely well defined.